Okay, so we want to get started with this Electrostatics 1, the very first free response question that was asked, and it's the only free response question asked in this packet. So if I can get this thing to cooperate, we're going to go right to there. All right. So here's what we know. We have two charges, a large positive charge above the y-axis, a large positive charge below the y-axis. They're equal distances above and below. That distance is A. And then out here on the x-axis in the positive direction we have a point P in space. And at point P in space right now there's nothing. And the distance from the origin to point P is 2A. Okay. So part A says, in terms of the given quantities and fundamental constants, determine the electric field at the origin. Okay. Well, part 1 wants the electric field at the origin. Well, if you look at it, electric fields go away from positives toward the origin, away from this positive toward the origin. The distances are the same, the charges are identical, so the electric field at the origin has to be 0. There is none. They cancel each other out because it's a vector quantity. Now we want the electric potential at the origin. Well, the electric potential is a scalar quantity, and so it is B for electric potential is equal to K Q over R. Well, we have two of those, so we're going to have electric potential because of this and because of this. So we're going to have two that are K, Q, but Q is a big Q this time, so I really need to follow what their symbols are. And the distance R from here to here is just A. So that one was pretty simple, not a real big deal. We got that one. It's all good. Okay. Now we're going to scroll up and figure out what's going on with part B. And it's been so long since I've done these, I'm really struggling with trying to remember what to do to go here and there, but we'll get it. Okay, so part B. Part B now says a small negative charge is placed at point P. Okay, so let's draw that. So a small negative charge. So here is my Q. Here's my Q. And here's my little small negative charge over here. And it's distance 2A away. And it's a negative small q. And this is my A distance. And that's my A distance. And they want to know, first of all, sketch an arrow indicating the direction of the electric force acting on the negative charge. Well, the negative charge is being pulled this way by that positive, and this way by that positive. So this vector force is going to be resolved into a positive y and a negative x. This vector force is going to be resolved into a negative y and a negative x. These will cancel each other out because they're identical in size. So the electric force acting on the negative charge is simply to the left. Okay? Now the electric field, well, let's get rid of this stuff here, these little red lines, see if we can get rid of these. The electric field is again a vector quantity. Electric fields go away from positive charges and toward negative charges. So if I can get rid of most of this red, we'll switch colors. So let's go to green. So electric field goes away from positives and toward negatives. Away from positives and toward negatives. So that E is made up of this component and this component. This one is in positive y direction, negative y direction, so these are going to cancel. So the electric field on this negative charge is simply toward the negative charge. Okay, so that's all they wanted me to do on part B. Okay, part C is they want some math. So let's figure out what we can do with part C. Well, if I can scroll it up, it says, determine the magnitude of the electric force at point P in terms of the given quantities in any fundamental constants. Okay, so we already know that at point P we have that little negative q. And we know that it experiences a force in that direction. And it's made up of, this is actually the force and this is the force, but we said that these components would cancel with that one right there. And so this I'm going to call Fx, and this I'm going to call Fx. And these two Fx's add up to give us that force. So the net force is going to be 2 times whatever we figure out the value of Fx is. Okay, well let's just get this plain old F right here. I'm going to call that F net so I can keep them straight. So that force right there is going to be K, big Q, little q, over however far apart they are. Well, if you remember, this was A, and this was 2A. So this distance from here to there is going to be the square root of 5A. Where did she get that from? Well, Pythagorean theorem, A squared plus B squared equals C squared. So that's 4A squared plus another A squared is 5A squared is C squared. But I just want this distance, the hypotenuse C, so I'm just going to say that that's radical 5 times A. Alright, so that's going to be the square root of 5 times A. So that's the hypotenuse, but I don't want the hypotenuse. I want this Fx, so I need a theta there. Well, that cosine of theta is the side adjacent, which we said was length 2A, over the hypotenuse square root of 5 times A. Those will cancel. So that'll be the cosine times the 2 over radical 5, because that right there is cosine of theta. And that will give me Fx. So when I do the math, that becomes 2k big Q little q. Alright, a radical 5 times a radical 5 is going to be 5a. So there's Fx, but I have 2 of those. Oh, sorry, that should be a square root of 5a. So let me fix that real quick because that'll mess you up. Square root of 5 times a. So I get 4k big Q little q over radical 5 times a is the net force. And it's to the left, but they only want the magnitude, so I don't really even have to tell them that because see it says determine the magnitude. Alright, and then we got a part D to do. So let me get rid of all that fun stuff, and then I'm going to go to the mouse and scroll down to part B, which is right there. Alright. So it says the negative charge is released from point P and allowed to move freely. So here's point P, and there's my negative Q. Alright, and we said that there was a force like that and a force like that, but that the components here and here canceled, so it really experiences a force here. So what's going to happen is it's going to accelerate toward the origin. So the negative Q will accelerate. Let's call it speed up as it approaches the origin. Now, once it gets to the origin, if you think about it, if this is the big Q, this is the big Q, and this is a little q, when it's at the origin, this is what happens. It's pulled up and it's pulled down, so the net force is 0. But so it no longer accelerates, but as soon as it gets past the origin, let's say it's over here now, this one's going to pull it and pull it. And so then I have a force pulling it back to the right. So it slows down. Negative Q. Oop. Sorry, that looks terrible. Slows down once it gets past the origin. It's going to come to a stop, because those forces here are trying to pull it back that way, so they're retarding the motion. Speed up as it returns to the origin. Okay, it now goes past the origin. back to point P, because again the forces are pulling it in that direction, past origin, to point P. It'll stop, and the cycle will start over again. So it really becomes like a simple harmonic motion. Cycle starts again. So really, you could just tell them that if you were answering this on the AP test, it just oscillates back and forth between point P, which is, okay, if this is my origin, and then it goes over this way, negative 2A. So it heads out, stops, reverses direction, stops, and that just keeps going. So it really just exhibits simple harmonic motion. It's an oscillator. All right, I'm going to post this one.